Right. So I'm Giorgia Vattiato. I'm a quantitative wildlife modeler in the wildlife modeling and ecology team at Manaaki Whenua. And yeah, today I will present some of our modeling results on how ship rats might respond to climate change in beech forests. These are ratting on a beach, which is not a beech forest, but who knows, maybe the seas will rise high enough. Right. So just an outline of this talk. I will first give a bit of a outline on what we mean by climate change effects and what those effects will be looking like in New Zealand. I will then present some of these effects of climate change on beech seeding, and then how ship rats in New Zealand's beech forests are going to react to that. And then I will present a couple of case studies that we've picked to look at ship rat dynamics in two different New Zealand regions. I will present the simulation model that we've used, as well as the model inputs and results. And I will finish off with some model limitations and possible future steps. So when we talk about climate change in New Zealand, and this has been briefly discussed as well in previous presentations, but looking at NIWA's climate change scenarios, we're expecting an increase in mean annual temperatures, as well as a decrease in the number of frost days and an increase in the number of hot days, so more extreme events. And also, we are likely to see an increase in precipitations, especially in the west and south of New Zealand. So how will these climate change metrics will affect beech forest and beech seeding? So I've used the same image as Adrian.
Georgia, I can't see your slide changing. I don't know whether anyone else can.
Oh, sorry about that. Okay. Right, I've gone through these. I'm here now. Thank you so much, Adrian. Right, so yeah, I was just saying I've used the same image as you, Adrian, to show some of the evidence that's been found on the effect that increased summer temperature and precipitation might have on seeding in beech forests. We're also expecting the frequency and intensity of mass seeding to change through climate change. However, all of these effects of warming temperatures and increasing precipitations and all that are still quite uncertain. So all we can do is make some assumptions on how climate change will affect beech seeding and in turn rodent population dynamics. So as most of us know, rat populations in beech forests are mainly driven by resource pulses. So if there's a lot of seeds, we also see a lot of rats normally. There is evidence of higher ship rat detections in warmer, low elevation beech habitats compared to the colder, high elevation ones. And Susan has presented it very well before. These differences is not only due to seeding, but potentially also to generate lower amount of resource and prey. There's less invertebrates. There's less insects and generally a less diverse resource pool for the rat. So in summary, what we know is that ship rats are usually found in warm habitats with an abundance of both seed and prey resource. A warmer and wetter climate will likely modify beech seeding dynamics and will likely result in a high rate of high flowering, so masting events. And we expect rats to be more likely to migrate to and potentially even remain in higher elevation beech forests if these start producing more seeds more often, or even if the the ecosystems of these higher elevation forests might changes with the warming climates over many years. So this leads us to two main questions, which are quite big questions. First of all, how can we model the effects of climate change on beech seeding dynamics? And Adrian has presented on that just before. And then how can we quantify the effects of these beech seeding dynamics on the rat population dynamics? So how are rats affected by these changes? What we've done is we've picked two regions in New Zealand. There are two 25 kilometer by 25 kilometer regions. One, which is a colder region in the North Islands, just west of Mount Ruapehu, and then a warmer region in the South Island, in southern Kahurangi region. And what we've done is we've split these regions into a cell grid. So each pixel that we are considering is 500 meter by 500 meters. And each of these pixels is defined by a forest type, a mean summer temperature, a mean spring rainfall. And then these inputs are then fed into Adrian's resource model, which will then be used to calculate our population dynamics using a differential equation model. So the model inputs that we're using, as I was saying, are the forest types of each of these pixels. This is just an overview of New Zealand's habitats, specifically beech versus non-beech. And then we're also using the mean summer temperatures and spring rainfall predictions extracted from Whenua's climate change scenarios. So we are, as Adrian has mentioned before, we're using these two scenarios, one slightly less pessimistic and one slightly more pessimistic. And here is just below is just a graph with an example of our simulated random temperatures that have been drawn from a distribution centered at these Whenua predictions. So, for example, our North Island region looks like this when we split it by forest type. So we have a different forest type for each 500 by 500 meter pixel. And then we overlay that with our temperature raster, which, as you can see, has got a different resolution. So it's Whenua's predictions are done at the 5 by 5 kilometer resolution. And so this North Island region is a bit colder. Our baseline summer temperatures range between 12 to 20 degrees Celsius. And then our worst case scenario in 2090, we see temperatures up to 26 degrees. And then if we look at the southern Kahurangi region, so the warmer region in the South Island that we've considered, this, as you can see, is a much warmer region to begin with. So our baseline temperatures range between 17 and 22 degrees approximately. And the worst case scenario in 2090 sees temperatures that go even above the 26 degree mark. So here's the model that we've used. I'm not gonna bore you too much with the equations. I'm happy to go back to them later for the maths nerds, but basically, this is a climate-based consumer resource model. It is based on the one from the Holland 2018 paper. It takes, as I was saying before, summer temperature and spring rainfall as inputs, or rather, we first draw some random temperatures and rainfall values from normal distributions centered at the Whenua predictions for each year. We then feed these predictions into Adrian's interaction model of beech mass seeding to get a yearly amount of seedfall for each pixel. And we then feed that yearly amount of seedfall into our differential equation model to calculate population dynamics. So for example, here is just a singular realization of our model, where we had simulated some temperatures. We've drawn them from that distribution centered at the Whenua predictions. And those temperatures were then fed into Adrian's model to get the total yearly resource, which is then distributed across the year in pulses. And below, you can see the corresponding rodent dynamics. So in black, we have a mean density across all the beech forest cells, and then in red they're just the peak, so the maximum densities that we were seeing in each day simulated. Now, what's interesting about this model is we can use it to observe what could happen if we see subsequent, say, masting event or different resource dynamics and how that would affect rodent populations. So for example, here we have another example simulations over 8 years. And this is quite interesting because we had a big mast year followed by a slightly smaller resource here. And the big mast year resulted in the rats population not crashing as hard in the inter-season period. So the rat population started off from a higher baseline, which led to a much higher peak here at the end compared to the previous ones. So for example, in the previous year, in say the 2062 year there, we had a similar amount of resources in the 2065, but the rodent density peaks are quite different because of that. And here is another example where we have several high masting events. Obviously, as Adrian mentioned as well, it's unlikely, at least today, that we see several years of subsequent masting events. But it's interesting to look at what would happen if. So here we had, for again, two sort of similar resource peaks. We see very different rodent population peaks because of the higher baseline that we start from subsequent high masting event, a high seeding event. And you guys have already seen this in Adrian's presentation. I just thought it was interesting to see that, yes, indeed, we are likely to see more high seeding events in the future, subsequent to as a result of climate change. So some of those scenarios that I was showing before are not that far-fetched in terms of potentially seeing a lot higher baseline of rat population densities as climate warms up and gets wetter. So here are all of our results on population dynamics under the different scenarios of climate change. I don't want you to focus on the actual numbers more than the trend that we see. So some of these the notable results, which are quite intuitive, though, is that we see an overall increase in the expected mean and peak rat densities in beech forests for each climate change scenario. Obviously, the more pessimistic scenarios see a higher ramp up in those population dynamics, population densities. And like we were showing before, there's also a higher probability of masting with climate change, which could possibly lead to higher rodent baselines and peak densities in beech forests. And it could also be interesting to speculate that those higher mean temperatures overall might change the ecosystems in what are currently colder beech forests, and changing the ecosystem might change those baseline rodent population numbers. So some of the model limitations and some of the things that we're planning on doing next is we're first going to add an elevation layer, which will, as Susan has presented before, will most likely affect that, which affects rodent population dynamics. So we're expecting at high elevation potentially to have lower baselines or bigger crashes of the rodent populations in between seeding events, mainly because they can't feed on other things, maybe birds. And then it would be interesting to use the elevation layer potentially in the future to look at effects of pest control at different elevations, whether it's more interesting to control them down low or higher up, or at what time, as Joe was mentioning as well. We might also add an immigration term based on cell attractiveness, with rodents most likely to move to less crowded, higher resource regions. We could also add an interaction terms between rats and mice between the different rodents, because we know that rats also predate on mice, so they might their populations are affected by what mice are doing. And finally, we obviously, as for all models, we always want to try and parameterize them better, make them more realistic. So collecting more data on the different drivers and dynamics of rat populations is always interesting to do. I think that is me. So thank you very much.